covering chemical bonding from the AS level syllabus. We'll be looking at the shapes of molecules. The concept that is involved here is known as valence shell electron pair repulsion theory. So this basically states that in the molecule, the electron pairs in the outer shell repel each other, and therefore the shape of the molecule is determined by the repulsion of the electron pairs in the valence shell of the central atom. In order to determine the shape of the molecule, you need to determine the number of electron dense regions around the central atom, which are also known as bond pairs and lone pairs. The bond pairs are the electron pairs in the bond. So if there's one line, then that is one bond, and therefore there is one bond pair. And a lone pair is a pair of electrons that is not involved in the bonding. Next, you need to determine from this information, you'll determine the electron and the molecular geometry, and this will give you the shape of the molecule. Our first example is boron trifluoride. And now all of these foundational examples are available in the syllabus, and these are supposed to guide you in order to determine the shape and the bond angle of newer examples that you are given in an exam. So boron has three bond pairs because it forms three bonds with three fluorine atoms. So the bond pairs, they arrange themselves with maximum distance between them. This means that because of the repulsion, they're going to arrange themselves so they're as far apart as possible. That gives us a bond angle of 120 degrees. So the shape is known as trigonal planar. The next example is methane. So in methane, you have carbon bonded to four hydrogen atoms. There are four bond pairs, and so you have a 109.5 degrees angle, which is known as the bond angle, and the shape is known as tetrahedral. The wedge that you see right now, it basically means that the molecule is basically a 3D structure, and the wedge means that the bond is coming towards you. It's coming towards you, and the dotted line means that the bond is moving away from you and away from the plane or away from the screen. And the single line means that it's the bond is within that same plane. Now, this is a way to show a 3D arrangement of a molecule. So in our earlier example, boron tetrafluoride, all of the bonds were in the same plane, but not in methane. In methane, you see that bonds are in different planes. And the dotted line in the wedge is used to draw this on paper. Now we look at phosphorus pentafluoride with 5 bonding pair of electrons, and again a 3D arrangement. To maximize uh, to maximize the distance, we again have 120 degrees and 90 degrees of bond angles, which gives rise to a trigonal bipyramidal shape. Next, we have sulfur hexafluoride. Sulfur hexafluoride has 6 bond pairs, and so it has a 3D arrangement with 90 degrees bond angles as the bond pairs repel each other, and the shape is known as octahedral. Now, what about lone pairs? We've looked at 3, 4, 5, and 6 bond pairs, but what about lone pairs? Well, when we have lone pairs, the electron geometry is the same as if there were only bond pairs present, or if as if you would consider the lone pair as being a bond pair. But when you look at the molecular geometry, you have to change it slightly by accounting for the lone pair repulsion. So according to the valence shell electron pair repulsion theory, the most to the least amount of repulsion is as follows. The most repulsion is between the lone pair and the lone pair, and then lesser repulsion is between lone pair and bond pairs, and the least repulsion is present between a bond pair and a bond pair. This will, of course, influence your molecular geometry, not your electron geometry, and it will influence the shape of the molecule. So firstly, we have ammonia as an example. There are 3 bond pairs in ammonia and 1 lone pair. So the electron geometry of this would be guided by how many electron dense regions are around the central atom nitrogen. We have four electron dense regions, and so we'd have the same electron geometry as methane, which is 109.5 bond angle and a tetrahedral shape. But now we have a lone pair instead of something that gives us equal amount of repulsion. And because of that, because all the bond pairs are repelled more by the lone pair than by each other, it would compress the bond angle and result in a 107 degrees bond angle rather than a 109.5 degrees bond angle. This gives rise to a new shape known as pyramidal because it looks like a pyramid. If you imagine all of this in a 3D arrangement. Now let's look at water. It has two bond pairs and two lone pairs. The bond angle is compressed even more than in ammonia, because it has two lone pairs, this reduces the bond angle to 104.5 degrees and gives rise to a new shape known as nonlinear or bent. Now we have double bond cases. So each double bond can be considered as a region of one region of electron density. Looking at carbon dioxide, each double bond can be counted as one region of electron density, and so there are two regions of electron density. When they arrange themselves with at maximum separation from each other, they have a bond angle of 180 degrees, which is also linear.